Okay, let's talk about solution preparation and dilution. So I'm going to start off with an example. So in this example, I say what mass of calcium bromide is necessary to prepare 175 milliliters of a 2.15 mole calcium bromide solution. Okay, so we're looking for the mass of our calcium bromide. I guess I can label that better. Mass of the calcium bromide necessary to prepare 175 milliliters, 2.15 calcium bromide solution. Okay, so we could look at the molarity, a little bit different, and that's usually what's helpful. So the molarity, when we write 2.15 molar, that's the same thing as 2.15 moles calcium bromide per liter of solution. Okay? So when you write it like that, you can see a little better that that's basically a conversion factor between moles and liters. So if you realize that, and then you see you have milliliters, if you convert the milliliters to liters, then you can convert the liters to moles using the concentration, and then you can convert moles to grams using a mole. Alternatively, if you didn't want to use dimensional analysis for everything, then you could think about, well, molarity, I can set up an equation. Concentration is moles, which we represent as an N over volume, okay? And you have the concentration and you have the volume, so you could solve for moles. And then once you have those moles, you could solve for grams, okay? So either way would work. Now I'm going to go the dimensional analysis route. So I know that I can use the molarity as a conversion factor. So I'm going to start with the other number, the one that's not a conversion factor, 175 milliliters, okay? And in order to use my conversion factor, molarity, I need to get that in liters. So that's going to be what I do first. I'm going to convert the milliliters to liters. And 1 liter is 1,000 milliliters, or 10 to the third milliliters. So my milliliters cancels here. Then I can use my conversion factor to go from liters of solution to moles of the calcium. So that ratio, moles to liters, that's just a molarity. And so it's 2.15 moles per 1 liter. So that's going to cancel my liters. And then my moles I can convert to a mass using molar mass. So I can get rid of moles of calcium bromide. I can go to grams of calcium bromide by using the molar mass. So I need to look up on the periodic table. If I look up calcium's 40.08 grams per mole, I have 2 bromines, each one of those is 79.0 grams per mole. So I add those together, and let's see what I get. Looks like 199.8 grams per mole. So that I can put into my ratio 198. So let's see, per 1 mole. Then I can type this all in my calculator. 175 divided by 1,000 times 2.1 times 198. And let's see, looking at all those values, the 175.0, that's 4 sig figs. The unit conversion between milliliters and liters is exact. The molarity, the 2.15 is 3 sig figs, and the molar mass is 5. So the fewest there is 3, so I'm going to round to 3. And so I would get 75.2 grams of calcium bromide. Okay? And so that's the mass I need to prepare this 175 milliliter solution of 2.15 molar calcium bromide. But once you've calculated this, you need to know what to do with it. So you need to think about, if you were to go in the lab and actually need to prepare this solution, what do you need to do? And so basically what you would do is you would get what we call a volumetric flask. Okay? So it's these flasks that have this long, narrow neck. And on that neck, it has one measurement mark. And that's for a very specific volume. And in this case, we wanted to make what? 175 milliliter solution, so we would have to have 175 mil volumetric flask, meaning that measurement marking would be 175 mils. Okay, and then we would take that 75.2 grams of calcium bromide and we would put that in the flask. Okay? And then we would add water. Okay, and you'd add water until you create that 175 ml solution. But as shown here, you actually wouldn't add it all at once, okay? If you're starting with this solid solute, what you would do is you would add some water, you'd put the lid on, and you would invert it, you'd shake it until you get all that solid to dissolve. And then you would fill it up to the mark with water. And the reason you do that is because when you're trying to get that solid to dissolve, it's going to require mixing. If you fill it with water right off the bat, it's harder to mix it with that smaller air bubble. So sometimes there's a little bit of volume change as you mix solids with liquids. And so if you fill it to the mark right to start with, that might cause you to overfill it and not realize it. So you got to be careful with that. But basically, you should be able to calculate how much stuff you need to prepare a given solution if you know what concentration you want and you know what ending volume you want. And then you should be able to take that information, that mass that you calculate, and actually prepare a solution using that. Now, one other thing that we do with solutions is there's lots of times instead of preparing a solution from a solid, okay, we could be preparing it by doing a dilution, okay? So you could have a solid and you combine it with water to prepare something. Of course, there you have to quantify how much of that solid you're going to need. But on the other hand, if you're doing a dilution, that means you already have a solution, but it's too concentrated, okay? And a dilution is the act of reducing the concentration of a solution. And to do this, you add solvent. And when you add solvent, of course, the solution volume is going to increase, okay? But the amount of solute that's in there stays the same, okay? That remains constant. So you're adding solvent, thereby the solution is increasing, but the solute remains the same because you're not adding, you're not taking anything away. So with that, we can actually create an equation that helps us quantify how we would do a dilution, like how much stuff we would need or what concentration we're going to end up with. Okay, so we do this using the molarity equation, okay, because we're pretty much always dealing with molar concentrations. Now you can utilize this actually for other concentrations, but we're going to focus on if we had a certain molar concentration or if we wanted to dilute to a certain molar. So what we have really when we perform a dilution is really kind of two solutions. You have an initial solution that has a certain concentration, and you have a final solution that has a different concentration. So we can set up that molarity equation as an initial set of parameters and a final. So the initial concentration is going to relate to an initial number of moles and an initial volume, whereas the final concentration is going to relate to some final number of moles and some final volume. Okay? And as I already said, the solute amount remains constant, so your number of moles stays constant. So the Ni must equal the Nf. Okay? That means we can take those two equations, rearrange them to solve for the moles, and then we can set them equal. So we rearrange them to set them equal to moles, okay? So, or to solve for moles, sorry. So Ni equals Ci times Vi, and then Nf equals Cf times Vf. And it's just rearranging those first equations. And then we can set them equal to each other since the moles are equal. So we get an equation CiVi equals CFVF. That's going to relate the initial and final concentrations with the initial and final volumes of those solutions. Now, sometimes you'll also see this written as C1V1 equals C2V2. That's fine as well. Or it may be written as M1V1 equals M2V2. That's fine as well. All of those, it's the same thing. It's just some people write it a little bit different. But mathematically, it's all the same thing. But we can utilize that equation to solve for any one of those four things if we know three of, the other three. So I've got a couple examples of how we would utilize this relationship. Okay, so we'll do a couple calculations to predict how we can do a dilution that we want to do. I guess before we do that, let me talk about kind of the experimental process. And as we do the calculations, then I can refer back to this. So when we do a dilution, remember, we're starting with some concentrated solution, and we're going to take that and add solvent. But most often when you do this, you don't just take that concentrated solution and add water or whatever the solvent is. You take a small portion of the concentrated solution and you put it in another container. Okay, that's what they're showing there in the first picture, taking some solution out of that flask with a pipette, and then they transfer it to that second flask and put some of that concentrated solution in, and then they add some water, mix it, and then finish adding water to the final desired volume, okay, to get the dilute solution, okay? So you normally wouldn't take your entire stock solution and dilute it. You'd take a small quantity of it, whatever you need to prepare the final solution. Okay, so let's look at a couple examples. In this first one, I say a 5 ml aliquot of an 18 molar H2SO4 solution is added to an empty 250 milliliter volumetric flask. And then the flask is then filled to the calibration mark with pure water. What's the new concentration of H2SO4? Okay, so there's some terms in here that I know kind of throw people off sometimes. So when we say a 5 ml aliquot of 18 molar H2SO4 solution is added to an empty volumetric flask, well, you're taking a 5 ml portion. So you have some 18 molar H2SO4 solution, a large bottle of it or something. You have way more than you need, and what you do is you take a 5 ml portion of it, or a 5 ml aliquot, and you're putting that into a different flask. You're putting it into a flask that is meant to give you an ending volume of 250 milliliters. Okay, so a 250 ml volumetric flask. You transfer that 5 mils, and then you add water until it is filled to the 250 mil. Okay? So we have three values here, and we should be able to solve for the fourth. And so it would be helpful to kind of organize the information with your initial and your final. Okay, so your initial, you have 5 mils of that initial solution, and it's an 18.0 molar solution. Okay, and your final solution is going to have a volume of 250 milliliters. And your final concentration is what we're looking for. Okay, so we're looking for C2, or CF, if you want to label it that way. Okay, so we can use the dilution equation. That's what I had on that previous slide here. This is what I would call the dilution equation, or in either of these forms, doesn't matter. And we're going to use that to perform this calculation, because really what we have, this would be V1, this would be C1, or I, and this would be V2, and then C2 is what we're looking for. And so I have C1 V1 equals C2 V2. I just plug in the information. So 18.0 molar times 5.00 milliliters equals C2 times 250 milliliters. Okay, now when you look at this, really the capital M is moles per liter. And so when you multiply it by milliliters, it's kind of weird, but you get millimoles. You could, if it makes you feel better, convert that volume to liters so that that product comes out in moles. And then the other side also convert to liters. And when you divide, you come back out with a molarity. But the nice thing about this equation, as opposed to the regular molarity equation, you can actually plug the volumes in different units. As long as the unit over here and the unit over here match. So as long as they're both in milliliters, it's fine. Or if they're both in liters, or if they're both in cubic centimeters or cubic meters. It doesn't matter what unit those volumes are in as long as they're the same. Okay, the same goes for the concentrations. We're going to utilize this for molar concentrations or molarities, but you could plug in, say, mass percent concentrations in here, but it would have to be a mass percent on both sides. Okay, so you can plug different stuff in here, but we're going to stick to molarities and then volumes, and volumes will either plug in milliliters or liters, but it has to be the same on both sides. So to solve this, I multiply the 18 and the 5, and then divide over the 250. So if I divide by the 250 milliliters, I'd have to do that on both sides. And then that means the 250 cancels, and then the milliliters cancel. So what I end up getting is a molarity effect. So 18 times 5 divided by 250. And then my 18 molars, 3 sig figs, my 5 mils is 3 sig figs, my 250 is 5. So I'm going to round my answer to 3 sig figs. So 0.360 molar would be my final concentration, okay, of that diluted solution. Okay, now one other thing is a lot of times we don't just take a portion and dilute it and, say what concentration did it end up to. A lot of times we have a goal. We want a particular concentration and we calculate what we're going to need and get that. Okay, so let's look at a version that way. So here I say what volume of a 12 molar sulfuric acid solution is required to prepare 1.5 liters of 2.5 molar sulfuric acid. So we have a goal in mind. We need 1.5 liters of 2.5 molar sulfuric acid. And we have a 12.0 molar stock solution to work with. And so I want to know how much of that do I need to take and dilute to 1.5 liters. So my 12.0 molar is really my C1. And my 2.50 molar is really my C2. That's going to be my ending solution. And I want 1.5 liters of that ending solution. And so I'm asking how much of the initial do I need? So I would have 12.0 molar times my V1 equals 2.50 molar times 1.50 liters. And so I can divide my 12.0 molar over. So that cancels with this one, and then the molarity cancels. And so then I'm going to get a volume when I take 2.50 times 1.0 and divide by 12.0. And so all of those are 3 sig figs. My volume should end up in 3 sig figs. So my volume is 0.313 liters. Okay, so that's how much I need of my initial solution. So if I were to go in the lab to prepare this, I would measure out 0.313 liters of the 12 molar solution. I would put it into a flask that has a 1.5 liter volume mark, okay? And then I'd add water to that 1.5 liter. And that would prepare my diluted solution.